Welcome on this very snowy Wednesday, and I do have the whole family in the house, so I am going to apologize in advance for any interruptions that are surely going to happen. So I realized the other day that we didn't define what is a measurable function, and by the way, here notice that I've decorated our slides with a depiction of the Lebesgue integral, a graph where you can see it's the y slices we're interested in, and of course we'll go back down and look at the measurable sets, the inverse sets of the y slices, as Mike had talked about last time. And just for kicks, I have down here the Lebesgue integral. So what is a measurable function? Well, it has a very formal definition. A function f going from r to r is a Lebesgue measurable function. And by the way, you don't need it going from r to r, but I want to keep things centered for the purpose of partial differential equations. But in this case, we have it going from r to r. It's a Lebesgue measurable function. If for each parameter a in the real numbers, the set formed by f of x smaller than a, so you can think of this as slices in a sense, which is really the inverse of these slices, is a measurable set. So an example that we've looked at already is if we look at the characteristic function over the rationals, that's a measurable function because the set where if you took any slice it would be a measurable set, but it's not continuous anywhere, so it's a very interesting function mathematically. I encourage you to prove these properties by using the definition of measurable. I'm not going to hold you to it, but if you want to include them on your exam 3, I encourage you to do so. First, if f is a measurable function, then so is a constant multiple of f, so is f squared, and so is the absolute value of f. All three of these are measurable functions. And I'm going to talk in a second how you would prove that. We also have that sums of measurable functions are measurable, the composition of measurable functions is measurable, and the maximum of two measurable functions, pointwise maximum, is also a measurable function. Number 6 is kind of weird, so I wanted you to think of it with an example. A lot of these ideas you want to think of with specific examples. So if I had f of x equals x squared and g of x equals x cubed, for example, and I graph both of them, this is a horrible looking graph, but it's a graph of x squared and x cubed on the same graph. If I trace out pointwise which function was the maximum, well, in this case, with the red, I'll see that x squared is actually the maximum until x equals 1, and then the x cubed takes over and becomes the maximum. So the red curve that you're left with is the function that represents the maximum, the pointwise maximum function of f of x and g of x. So how would you prove any of these theorems? Well, you must show, for example, like if I take the first one, if I take h of x equals the scalar multiple of f of x, and I form the set of x such that h of x is less or equal to a for a fixed a, I have to show that this set is a set that belongs to the sigma algebra. What you know, so this is what you have to show, what you know, your hypothesis is that f is originally measurable, so you do know that the set of x belonging to R such that f of x is less or equal to a is already in the sigma algebra. And you'll use that to get your show. So that you would do this for every one of the properties. Now, obviously, the last one that I showed you is probably maybe one of the more difficult ones, number 6, to prove. So I'd like to cover what I mean by a pointwise limit more rigorously. I talked about it last time. If I have a sequence of functions going from the reals to minus infinity to infinity, so I have each of them fn would represent a function, then the pointwise limit represents the limit when I fix a particular x and I take the limit of these fn's of x's pointwise, is referred to as a pointwise limit of the sequence f of n. Now that limit doesn't have to exist, so we talk about this limit in the case that it actually exists. So for example, what would the pointwise limit of the sequence of functions f of n of x equals x to the n look like? I can start graphing all these x to the n's and seeing it. So this here is x to the 1 power. This is x squared, x cubed, x to the 4th, x to the 5th, x to the 6th, and then I think I did x to the 20th, and this is x to the 200. And you can see these curves are all leaning down so that as the pointwise limit, each of these points are being sucked down to 0, except this piece right here at x equals 1, that remains at 1. So these continuous functions, pointwise, converge to a discontinuous function in the limit. The limit may not exist. I could take a sequence of functions fn of x equals -1 to the n times cosine x, and I'm just going to restrict it over 0, 1. You can see that you'll get the first curve, this one right here, every other term, and you'll get this maroon curve every other term. So if I took a point, like I fixed a point, point 2, you'll see it'll flip-flop between these 2 points, the y values. So because it's oscillating, it'll never converge. Though the limit may not exist, from real analysis we know of the 2 quantities, the lim sup and the lim inf, both do for the point. So I can definitely, if I don't have the limit existing, I can definitely talk about the lim sup and the lim inf. And it turns out that the lim sup of a measurable sequence of functions, that pointwise limit for each x, so you get a sequence for each x and you can talk about the lim sup, that function turns out to be measurable, as does the lim inf pointwise. And I'm going to stop the module here and continue on and separate these.